Nerve-wracking silence.
Yes. People will start joining. Right. Yeah. Balarka, I'll give you a sign, maybe like quarter two, if you're not done by then.
Okay, sure.
Just so we have a little time for Q&A and you don't get it all once you're
Please.
offline.
Yeah, I mean, we have this tendency of getting carried away and then plowing on, basically. No.
Me too.
Just shut the microphone if you can. That's fine.
Well, you still need to answer questions.
Oh, yeah, of course. Yes. Yeah. Yeah, I'm not going to run away. Yeah, I might.
Not fall asleep.
Yeah.
What time is it? 9?
It is approaching 9, yes.
Hi, everyone. For those of you who are already on the line, we'll be waiting for another couple of minutes before we get started. Thank you. All right, let's go ahead and get started. My name is Julia Matevosian. I'm Associate Director and Chief Engineer at Energy Systems Integration Group. ESIG also serves in a leadership role with Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze rapid clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across 5 action pillars. The foundation of G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner as other system operators in the world. The 5 pillars of consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. ESIG is a lead on Pillar 1, and more information on G-PST can be found at www.globalpst.org. As the lead of Pillar 1, ESIG would like to welcome you to the November monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to regular ESIG monthly webinar series and focuses on G-PST research agenda and associated topics being presented in Pillar 1. The topics are being presented by system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in activities of Research Agenda Group and Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org, click on Get Involved tab, and further information on ESIG and ESIG's webinars can be found on www.esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, we'll use a Slido platform at slido.com. You need to open a browser window, go to slido.com and enter ESIG21 as an event code. The instructions are also at the bottom of the screen right now. You'll see a thumbs up button next to the questions in Slido to allow you cast your vote and help us prioritize questions. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with link will be provided once the video has been posted. We'll also plan to provide short responses to unanswered questions after the webinar. So please don't be afraid to ask your question through Slido. All right, so the topic of our webinar today is IBR-driven sub-synchronous oscillations, certainly an important and timely topic with growing shares of inverter-based resources that we are experiencing around the world. During previous G-PST ESIG webinar in September, Nick Miller from Hickory Ledge has presented the work that he led at ESIG on diagnosis and mitigation of observed oscillations in IBR dominant systems. That resulted in a guide for practical engineers, and he provided an overview of the guide during the webinar. You can find a recording to the webinar and the guide on the ESIG webpage, and the link is now posted in the chat. So today's webinar will feature Balarko Chaudhuri from Imperial College London, who will continue the discussion on the topic of sub-synchronous oscillations caused by multiple inverter-based resources interacting across the power grid, especially under high IBR scenarios. The lack of an established framework for analyzing SSO makes it difficult for the system operators to foresee, as was exemplified by recent SSO events. This webinar will focus on IBR-driven SSO problem analysis and mitigation based on Imperial's ongoing research with National Energy System Operator, NESO, in Great Britain. And as a part of Global Center of Electric Power Innovation for a Carbon-Free Society, or EPICS. Balarko Chaudhuri is a reader for power systems in the Department of Electrical and Electronic Engineering at Imperial College London. His research focuses on dynamic stability and control of electric power grids with high shares of variable renewables and inverter-based resources to facilitate the transition to net zero carbon electricity. Balarko serves as a UK director for the Global Center of Electric Power Innovation and Carbon-Free Society, or EPICS, and is actively involved in stability assurance programs supported by National Energy System Operator, NESO, in Great Britain. He co-leads the workforce development pillar in Global Power System Transformation Consortium, where he coordinates G-PST teaching agenda and oversees development of openly available course materials on forward-looking topics for use in teaching and training and self-upscaling. I highly recommend that you go to G-PST webpage and look at some of these materials. Balarko is a fellow of the IET and has served as an associate editor of IEEE Transactions on Smart Grid, IEEE System Journal, and Elsevier Control Engineering Practice. All right, so just a short reminder once again to use Slido at slido.com with event code ESIG21 to ask your questions. And without any further ado, let's go ahead and get started. Balarko, I'll turn it over to you.
Thanks, Julia. Let me share my slides. I'm just trying to get it to full screen. Can you see my slides, Julia?
Yes.
I'm assuming if you can see it, the audience would be able to see as well.
Yes, definitely.
Okay, thank you, Julia. Thank you for that kind introduction, and thank you all for joining. I know for some of you, this could be well outside your normal office hours, so appreciate you making an effort to join. So the topic, as Julia introduced, is IBR, inverter-based resource-driven sub-synchronous oscillation. And the theme basically of my presentation would be how can we get to the bottom of these oscillations. And as Julia mentioned, Nick, who led the task force on diagnosis and mitigation of these oscillations in ESIG, gave a wonderful webinar, which was sort of comprehensive, touching upon all kinds of oscillations. Today, this is going to be very specific about IBR-driven SSO, and I'll come to a slide soon, which would be basically setting the scope, the exact scope of this webinar. But before I get into that, let me do sort of a round of acknowledgements, and I have to thank a lot of people and organization. Firstly, and most importantly, the researchers here at Imperial who are involved in stability of IBR-dominated grids, and my colleagues here from control, power electronics, and power system operation, who sort of all join hands to get this research on stability going. On the funding front, the work is mainly funded by UKRI and to a large extent by the National Energy System Operator, NESO, which is the electricity grid operator here in Great Britain, but now with much broader remit in terms of multiple energy vectors. And the work on stability services in particular is funded by Leverhulme through my colleague Mark O'Malley and Elena Spiro. The third element of this, our research, is the context or the buy-in from the stakeholders. And for that, we are really grateful to organizations like ESIG, Global Power System Transformation Consortium. Both of these bring together a lot of stakeholders, system operators, OEMs, and so on. And also for the context, I should thank NESO, our industrial partner, for those discussion around the problems that they see on the field. So this basically helps us set hopefully the right questions, the ones that are grounded in the real world problems. And then the final pillar of this is our collaboration outside Imperial. Mainly this is happening through EPIC's Global Center. EPIC stands for Electric Power Innovation for Carbon-Free Society. And this is a center which is funded by the research councils in Australia, US, and the UK. And there are multiple universities involved in this consortium from all those three countries, but the work on stability of IBR-dominated grids, we are working mainly with Johns Hopkins University in the US, Monash University in Australia, and Strathclyde here in the UK. At Imperial, we have a group who are working closely across these four areas: control theory, power electronics, grid stability, and planning, operation, and services. And most of the work is actually happening at the boundaries of these areas. So I'd show some of the colleagues who I closely work with. So Tim Green and Yunji Gu bring their expertise in power electronics into grid stability on one side. And then we have Janusz Bialek and Fei Teng, who are tying up stability with grid operation. And then we have Mark O'Malley and Elena Spiro, who work on planning, but are involved particularly in the form of stability services, where we sort of collaborate a lot. Key to some of the work we do is actually our colleagues in the control theory. For example, Thomas Parisini works in the area of digital twin, which is going to be, we think, the way we look at it, a key element to capture the operating point dependency of black box IBR models. So if we can have a digital replica of this IBR, we can hopefully track down the behavior closer to real time. Then Alessandro Astolfi and Giordano are experts in nonlinear control, and Alessandro is helping us with reduced reliance on post-fault simulation for large signal stability analysis. And then Giordano is helping us with his techniques on complexity reduction to go to develop accelerated EMT simulation to basically speed up and do many more scenario checks than what is currently possible in EMT timeframe. And then we have colleagues in power electronics who are not directly involved in grid stability, but are working on more of standalone microgrid applications or distribution network. And in case of Adria, he's also into high voltage DC applications, but less so on the grid stability part. Researchers, we have at the moment about a dozen researchers who are sort of dedicated on stability of IBR-dominated grids, and their focus areas are divided into these 4 categories. Starting from the top right, data-driven analysis, again, to get around this black box nature of IBR-driven problems. So we have Debraj and Gianli coming more from the control theory point of view, and then Uwe and Andreas working at the boundary of data-driven analysis and modeling. We have Balarko and Shergil, who are deep into model-based analysis and also control of IBR. We have 3 researchers, Thomas, Wangkung, and Zongda, who are essentially working on stability constrained operation at the boundary of stability and operation. And then 4 of these researchers, Agnes, Ambuj, Fatima, and Fateh, who are basically working on various forms of stability related services. And we, at the moment, as we speak, we are in the process of recruiting another 8 postdocs, mainly in the data-driven analysis and then modeling and stability constraint operation. So it's a decent group of researchers at Imperial that we're having, and this is across all forms of stability problems in IBR-dominated grids. But today's focus is specifically going to be on sub-synchronous oscillations, which is just one element of the overall stability problem. So the word sub-synchronous suggests that the oscillation frequency is less than the fundamental frequency, which could be 50 or 60 hertz. The way I'm trying to sort of bucket them rather than classify them is in terms of whether the sub-synchronous oscillation is driven by synchronous machines or it's primarily driven by IBRs. That's along the y-axis, and along the x-axis we have whether the sub-synchronous oscillation is localized, is confined within a plant level or in the close vicinity of the plant level, or is it sort of manifesting more at a system level or maybe wide area. So this could be the geographical or the electrical spread of the problem across the system. So these are relatively well-known stuff, the traditional sub-synchronous resonance, which is a phenomena with a thermal power plant evacuating power through series compensated line, sub-synchronous torsional interaction. I'm not going to get into the details of this, but just to sort of mention that these problems are relatively well understood. Within the synchronous machine electromechanical timescale, the inter-area oscillation, which is more of a system-wide problem. Again, I mean, we have well-established method for analyzing these kind of oscillations. SSTI sits in the middle because this is a case where a synchronous machine, a thermal power plant, is exporting power through an HVDC link, for example. So it's kind of driven by both, if you consider the HVDC link to be an IBR. Then we have the sub-synchronous control interaction problem, sometimes referred to as series capacitor SSO, which is IBR-driven, typically associated with type 3 wind farms evacuating power through series compensated lines. Again, this is IBR-driven, but more of a localized problem. Similarly, you could have oscillations within a IBR plant, like a solar farm or wind farm, which again is more localized. The one that I'm going to be talking about is on the top right, which I'm calling as IBR-driven sub-synchronous oscillation, but I'm Not sure whether this is the correct way to describe it, whether it's specific enough, because in a way, everything on the top half of this chart is actually IBR-driven SSO. So essentially, this is when multiple IBR plants are basically interacting across the bulk power grid. So I've seen several phrases being used to sort of describe this stuff where multiple IBR plants interact across the power grid. For example, sometimes it's referred to as weak grid SSO. Not sure if, again, that's appropriate, because sometimes it's not just the weak or strong grid that determines this SSO, but also the control bandwidth of the IBR themselves. Sometimes it's referred to as control-induced SSO, which again could be appropriate. I'm putting question mark because I'm not myself sure what's the best way to describe. Some people describe these things as wide area SSO because it sort of spreads across the system, and it's definitely not something which is local to an IBR plant. But again, I mean, I'm not sure whether we have a term for these things, but at least my intention behind having this slide is to make sure that I basically make the scope of this clear. So essentially, we're talking of multiple IBR plants interacting across the bulk power grid. Now, there are two very good references. Julia already mentioned about the report that Nick Miller produced, which has got much, detailed description of each of these. And this is only sub-synchronous oscillation. That report actually covers super synchronous oscillations. It's quite comprehensive. If you haven't gone through that report, I would recommend that. That's a very good read in this space. And then there was a paper published last year in IEEE Transactions and Power Systems, which covered many real-world examples, and they also talk about not so much the synchronous machine-driven, because that paper was specifically for inverter-based resource-dominated oscillations. So it's about the upper half of this graph. So we're going to talk about this today. And such IBR-driven SSO, there are more and more events being reported in the literature, especially from the sections of the system where there are high shares of inverter-based resources. And this is just one of several examples from Scotland. This is the infamous 8 Hz oscillation that happened there during the summer of 2021. Again, there's a lot of talk about this one. I'm not going to get into the details of any of this, but again, these are two excellent references. One came out early this year, and there are a number of SSO events that are reported with very useful insights in both of these papers. So the question is, can such oscillations be foreseen by the system operators? And the answer, well, I think I'm safe to say that not always, because otherwise these events won't be happening, and they are getting more and more frequent, as I mentioned. Now, in terms of foreseeing the risk of such oscillations, there are basically two things I would like to point out. One of the key checkpoints for this is the connection compliance process when an IBR plant is connected to the system. So the question really is that is that compliance process rigorous enough to capture the risk of these oscillations? And the second element is when we try to see or even replicate these oscillations in modeling, in a modeling simulation environment, whether our models that we are using are adequate. For example, if we consider the IBR models, do they have the level of fidelity that is needed and the specific sort of bandwidth, etc., of the control loops? So for example, we could use the vendor-specific black box IBR model, or we could use generic ones with some form of parameterization. But the key to see these oscillations or foresee these oscillations is that the model should be appropriate. And it's not just the IBR model, it's also the the simulation platform, for example, whether you are using an RMS tool or an EMT tool, or maybe a hybrid, where the section where there is high share of IBR could go in EMT and the rest in RMS, but then there are also some question mark about how do you sort of decide that boundary and so on. So overall, modeling adequacy is another key thing to sort of foresee or replicate these oscillations. And the second point is, even when such oscillations are actually seen in, let's say, a simulation platform, an EMT simulation platform, for example, or for that matter in real world, how to then analyze and find the root cause of these oscillations, find basically the bad actors, which IBR plants contributed to this problem. And then once that is hopefully dug out, we can then go for targeted and effective mitigation. So this is what I'm going to be talking about. And again, I would sort of point you to this reference that Julia mentioned. I've showed on the previous slide as well. This is a very comprehensive document on diagnosis and mitigation of variety of different types of oscillations, which are either seen in the simulation environment or in the from the field measurements. Okay, so I prefer to take a step back and look at how oscillations were analyzed for a traditional synchronous machine dominated system. We can take the example of inter-area oscillation because that was a system-wide problem. And for inter-area oscillation, there is established modeling and analysis framework. Many of you in this call are aware of that. Firstly, the models for synchronous machines are well established. The parameter range is also either you have the actual parameters, or even if you work with, let's say, the typical parameters, there is an established range which you can use. The network topology is assumed to be known in the form of the bus admittance matrix that you use for load flow. So basically, you can work up a differential algebraic representation of the overall system by having all the dynamic components, the synchronous machines, and any other dynamic components that you have in the system in the form of a differential equation. You can have the static components like the network, the static loads, and even the stator winding of the synchronous machine as algebraic equation. You can linearize these differential algebraic equations to form a state space model around an operating point, which is denoted by this suffix 0. And by doing a modal analysis or a small signal stability analysis on this linearized state matrix, you can actually get to the bottom of these oscillations. You can find out which synchronous machines or which other dynamic components are actually contributing to this problem. You can find the mode shape as well as the participation factor. So that's pretty standard. And so the question really is that to what extent we can get, let's say, close to this kind of a framework for an IBR dominated system. So in order to do that, first thing I want you to notice here is that for synchronous machine dominated system and analysis of inter-area oscillations, often, I mean, not necessarily, but often the framework that is used from the network point of view is the current injection model, where these are the generator stator currents, and then you basically do this algebraic operation and you get out the voltage at the terminal of the machine. Now, when we look at an IBR model, and essentially for this kind of wide area SSO problem, we are looking at aggregated representation of an IBR plant rather than individual IBR devices. And the interface of the IBR plant with the network, the way I'm showing it here, what we do is we consider an LC filter, and the voltage across that filter basically is the input to the network. The other side of the filter and the transformer is considered to be part of the network. Again, I mean, this is one way of doing it. We could also do it with an LCL and take the voltage of the terminal of the IBR to be the other side of that L component, but this is how we do the modeling. And if we do it like this, from a network point of view, this becomes a voltage injection, and then the network basically sets the current based on that voltage. So the closed loop system is like that, unlike what we saw for synchronous machine on the previous slide, where it was a current injection framework for the network. So input was current and the voltage was calculated based on the network element. So this is a subtle difference that I want you to notice before I go to the next slides. And then a quick look, again, I'm not going to discuss this in detail. The IBR control is the key, obviously, and there are various ways in which you can do this. This is the sort of the standard, if I can call it, the grid following control with an outer loop which is feeding the current control, and the PLL basically senses the phase angle and makes sure the current is injected at the appropriate phase angle. For grid forming, again, there are various ways. For example, you could do a virtual synchronous machine, you can do a virtual oscillator, or a droop control. For the results that I'm going to be showing later on, we have used GFM grid forming with droop control in this format. Okay, so an IBR dominated system would look something like this. We have the network here. This is a bunch of IBR 1 to N and the loads and the synchronous machines. So I'm going to be talking about three things in this context. The objective is to how we can obtain the overall, let's say, state matrix to analyze IBR-driven SSO following the template of analysis of inter-area oscillations. So first thing is the IBR plant models are vendor-specific, proprietary, and black box. So the structure of this differential equation that describe the dynamic behavior of the IBR is not necessarily known, the vendor-specific structures. But there are generic model structures that are available, but the parameterization of those generic models for different contexts could be challenging. At least it's not straightforward without extensive tuning and so on. And if the parameterization is challenging, it is not easy to track the operating point dependency of these linearized IBR models. So if you have to find the linearized model around an operating point, it's not straightforward unless you have proper parameterization of the generic model. And that's one thing. So I'm going to talk about how this can be approached. The second element is, now that we have an IBR dominated system with a relatively faster response than synchronous machine control system, the frequency of oscillations are typically higher than what we are used to seeing in synchronous machine dominated systems. So the next question is whether we can continue to represent the network in the form of algebraic equations or static equation, as is done in RMS tools, or do we have to necessarily use differential or dynamic representation of the network as well as the synchronous machine state current? So essentially, it's this discussion between use of RMS tools. Is it good enough, or when are the situations where we have to look for EMT, specifically for SSO analysis? And the third element is the aggregated load model. Again, for inter-area oscillation studies, there were certain form of aggregated load models that have been sort of, I won't say standardized, but those were being used quite routinely. But loads have changed. Now there is a dominance of loads which are exhibiting more of constant power behavior rather than constant current, constant impedance. So is it time to revisit the aggregated load representation at the boundary of transmission and distribution? So again, I'll talk briefly about a project that we are about to start with one of the transmission owners here in the UK, about specifically looking at how the grid supply point, which is an interface between transmission and distribution, should be modeled in stability and studies. So I'll go through 1, 2, and 3 for the rest of the presentation, and hopefully I'll it to the end. So this is the same diagram I'm carrying forward to the next slide. All I'm doing here is I'm taking one particular IBR plant. It could be any of them, let's say the mth IBR power plant, out of this, and I am having the rest of the system in this orange box. So it's the same diagram, just one IBR, the IBR, let's say, of interest is taken out of this block. And I'm representing this as a closed loop system where GIM is the, let's say, the model of the mth IBR. The output is voltage, input is current in the block diagram. And this GR is the rest of the system, which consists of the network, all the other IBRs apart from IBR-M, synchronous machine loads, everything else in the system. So it's just one IBR taken out in isolation and the rest of the system here. Now, this one is just for illustration. So what is done here is one particular IBR, in this case, a grid following inverter, is considered in isolation in standalone mode. And the GFL is controlled in active power and AC side voltage magnitude. So both of those references are set to 1 per unit. And the operating point for this IBR is actually varied between weak grid condition, a very low short circuit ratio, almost the static limit as far as you can go down, to decent short circuit ratio of 5. So the short circuit ratio is changed at the terminal of this IBR, and that would basically change the voltage, magnitude, and phase angle. And these are shown the D and Q axis voltage and the D and Q axis current of that IBR, the range that you will have if you vary the SCR is shown here. So if you plot the frequency response of this IBR for different operating points within this range, SCR of between 1.1 and 5.0, these are the family of curves you will get. And each of these trace on the frequency response basically represent a different operating point, which is sort of denoted by this range of short circuit ratios. And the top subplot is showing the D-axis impedance, if you like, and the bottom subplot is showing the Q-axis impedance. And you can see that there is quite a lot of variation in the frequency response as you change the operating point. And the question really is, how do we estimate the linearized model for each of these operating points, basically? Okay. So in these expressions and also on the following slides, the suffix 0 basically denotes an operating point. So it's the model which is linearized around an operating point. Okay, so in order to, basically the job now is to estimate the linear model of this IBR-M. And in order to do that, like you do for, let's say, impedance approach, here what you can do is you can inject a current perturbation, which is denoted by delta IM at the terminal of the IBR, and basically obtain the perturbed current, which is delta IM prime, and the perturbed voltage, delta VM, again at the terminal of the same IBR. So if this is a simulation model, it could be a very large system with lots of IBRs and the rest of the components. All you are doing is you are accessing the terminal of the mth IBR, injecting a current perturbation and measuring the perturbed current and voltage. Now, just by looking at this, one could be tempted to think that, okay, if I do that and if I can sort of estimate the model between delta VM and delta IM prime, I will get the estimated model of the IBR-M. Unfortunately, that's not as simple, because if you look at this, this is a closed loop system, and delta IM prime, which is sort of the current into the IBR, is actually dependent on this delta VM through this feedback loop. So if you use system identification to estimate or identify this IBR model by just doing delta VM over delta IM prime, this is not going to work in general because of the dependency of the input and the output. For system ID to work, you need independent perturbation. So if we want to identify the inverter model here, we could do the following, which is do two separate estimations. So in this, what is shown here is that you can definitely estimate or identify the system between delta VM and delta IM, because delta IM is always an independent input. It doesn't depend on anything else. So you can estimate this model. You can also estimate G-PST, which is between delta IM prime and delta IM. Okay? So it's between the perturbed current and the perturbation input that you apply at the terminal of the IBR. So you can estimate these two models separately. And if you now take the product of GS2 and inverse of GS1, basically you will have delta VM over delta IM times. So if you invert that, basically you get delta VM over delta IM prime, which is nothing but the estimated model of this mth IBR. Question is, okay, so this is the estimated model. Of course, this will only work if your GS1 is invertible. Now, thankfully, GS1 is always invertible, because if you look at GS1, this is the transfer function or the input-output behavior between delta IM prime and delta IM. So there is a feed-through connection between delta IM and delta IM prime, because there is no dynamics in this route. I mean, there's dynamics through the feedback, which means the feed-through matrix is always going to be non-zero for GS1. And once the feed-through matrix is non-zero, you can actually invert the LTI system transfer function. So it is always invertible. And the accuracy of this estimated model is going to be dependent on the nature of this perturbation, whether it is rich enough to excite the dominant modes that are present in the IBR and the closed loop system. So the key to the success of the accuracy of this kind of system ID technique is that your perturbation should be sufficiently rich. And I'll come back and make some comments about this. So the takeaway from all of this is that you can use GS2 and GS1, of course, everything around an operating point. This is all around a particular operating point. You can actually get an estimated model of IBR-M. Now, to validate the accuracy of this, we considered three different operating points as seen at the terminal of the IBR. So these are actually the power, that active power that's measured at the IBR terminal. And these are in response to a step change that you see in gray. So the first operating point is actually oscillatory. It's showing a 9 Hertz oscillation, and the damping is pretty low here. The second operating point is reasonably well damped. And the third one is actually very well damped. In fact, it's critically damped. And as we will see in the next few slides, this is actually the difficult one for system identification to work, because if you have such a critically damped response, it's very hard to sort of excite the modal response and get a proper system ID. But thankfully, even if this method is not accurate, this is already a very well damped situation. So it's less of a requirement to try and get to the bottom of this oscillation. So that's good. So the first one, which is poorly damped, what we are showing here is the frequency response of that mth IBR. The top subplot is showing the frequency response along D and Q axis from the actual model. And the bottom one is showing the same from the estimated model using that approach that I described. And as you can see from these two, they are pretty well aligned. And as a result of that, if you look at the step response, the closed loop step response, when you consider that IBR and the rest of the network, they are also pretty close. And as I mentioned, the accuracy of this depends mainly on two things. One, if the perturbation signal that you are applying is rich and it's sufficiently exciting in terms of triggering the modal response. And the second one, which is also equally important, is while the perturbation would have to be rich, the response should stay within the linear zone, i.e. you should not sort of drift away from the operating point, because this whole notion is based on linearized sort of linear system identification. So you need to make sure that you are not sort of applying a perturbation which is large enough to drift from the operating point that you are about to estimate, or you are estimating your model about, sorry. Now, in a simulation environment, these things are relatively easy to sort of achieve, because you can actually apply rich signals like multi-sign or pseudo-random binary signals, which are typically very rich in terms of frequency content. But applying such rich signals, let's say in a real world, is difficult because there are hardware implications of that. And also it is pretty easy, or relatively easy, I should say, to calibrate and make sure that the response stays within linear zone. It's small enough. But again, in a real world, when you have noise, it's a tricky trade-off. I mean, you have to be obviously above the noise level, but not sufficiently above so that you are drifting into the nonlinear zone. So, but the stuff that I'm showing here is in simulation, and there you actually can achieve pretty good results. The second operating point is the one which is well damped, and you can see that, yeah, of course, the frequency response is quite different, but the actual and the estimated are still very close, as we can see on this diagram. Move on to the third one, which is the critically damped. And here you see the big mismatch coming as we expected, because we don't have sufficient excitation of the poorly damped modes. And you can see the frequency response is drifting quite far apart. So if you do this approach for different IBR one at a time, you can sort of hopefully get from a black box to a gray box. It's still not a white box, because all you are doing is estimating the linearized model around an operating point. You are not sort of getting the actual state space model. But that would allow you to then use the approach that we have seen for synchronous machine dominated world and get basically the eigenvectors, which will give the mode shape and participation. So there are lots of questions about this in terms of the way I presented this. This is a sequential approach, but that means you will have to do one IBR plant at a time. Can we do it simultaneously? It is possible, but that would involve using a system identification with a block diagonal structure, which is difficult. I've talked about the issues with perturbation, especially when it comes to applying this in the real world, but in simulation, we can control things on perturbation and achieve good results. Scale up for large systems. Yes, I mean, we have to make this distinction that it's not the actual model that we are trying to estimate. We are trying to estimate the dominant modal response. And even if your model order is, let's say, 500, just as an example, this model could still exhibit a dominant sixth order oscillation, for example. So actually, this order of the estimated model is not going to go up with the system size. So that's good. Of course, again, noise is an important issue. Again, we are investigating that extensively in a NESO funded project, but we can have that discussion another day. So I'll quickly move on to the second aspect of this, which is how do we represent the network and the generator stator current. Again, I mean, this is a sort of a well-known issue. So we can use RMS type of simulation platform, which will allow us to do lots of scenario checks very quickly. But there is question mark even for SSO over the accuracy of RMS models. And then at the other extreme, we can go for EMT point-on-wave, which will be, of course, as close as we can get to the reality, but our number of scenario checks within a given time would be quite limited. There is middle ground in terms of EMT DQ in a synchronously rotating reference frame, and we can use that in time domain. It would be somewhat quicker than EMT point-on-wave because you're going to be overlook the sub-cycle dynamics. But if you can use EMTDQ to go and analyze in frequency domain, and that would be very quick in terms of scenario checks, because you can basically spit out the damping and frequency of this SSO very quickly. And we have done some benchmarking of EMTDQ and EMT-ABC specifically for SSO, and the results are pretty close actually. So if we look at the GFL, the grid following, these charts are showing the variation in damping ratio of the dominant sub-synchronous oscillation mode. If you use EMTDQ, that's the blue trace, and then the red trace is showing the RMS positive sequence. As expected, if you go down with short circuit ratio, the damping ratio actually goes down for a grid following. And if you increase the PLL bandwidth, which is the right side figure, the damping ratio also goes down. The point to note here is that if you use the RMS tool, it gives consistently the impression of higher damping ratio, pretty much irrespective of the SCR or the PLL bandwidth. So, and that's not unexpected, because what is happening is that in the RMS model, you are basically neglecting this differential term, and these differential terms are determined by two things. This time derivative is essentially related to the oscillation frequency of the mode, and usually when the control bandwidths of IBRs are high, this oscillation frequency tends to go up, which means it's going to create a bigger difference, as can be seen for higher PLL bandwidth. And also for a weaker grid, this L and CB would be typically large, and hence that would create a bigger difference that you can see for low SCR and high PLL bandwidth. And you can also corroborate that with the participation factor of the network states, which basically says the same thing. So the point to take away is that RMS generally shows higher damping than EMT, except maybe if you are at very low PLL bandwidth. And the difference is more exaggerated under weak grid conditions, low short circuit ratio, and high PLL bandwidth, or in general, I would say high outer loop bandwidth as well. For GFM, the variation is opposite. So it tends to sort of get more oscillatory towards high SCR, because it's a voltage source and they tend to fight when you have a strong grid. But the observation that the blue, the EMT damping ratio, is consistently below that predicted by RMS. And it's the same thing corroborated by the participation of the network states, basically suggesting that stability assurance with RMS could be misleading unless we are careful about this. And we then put them together in a small test system. This is the IEEE 39 bus, and all the synchronous machines replaced by IBRs. So with this composition, we have quite a high percentage of GFM by today's standards. And there is actually a lot of difference between the oscillation seen in EMT and the oscillation seen in RMS. But this is just one situation. The difference between this EMT and RMS will actually depend on the relative share of GFL, GFM, and also, more importantly, the control bandwidths. But generally speaking, RMS is not adequate in terms of capturing SSO. So this is the load one, the third element, the project that we are about to start with one of the transmission owners in GB. But for the sake of time, I'll just skip this one. This is to get sort of better aggregated representation of the transmission distribution interface. So I'll quickly spend a couple of minutes on this. So this is our 4-layer sort of defense against SSO. We are working with NESO and as part of the APIX Global Center. So the first one is IBR control design, because a lot of this SSO problem can actually be sort of mitigated at the source itself. But then it's always the design trade-off, because SSO is just one problem. And if the control design was specifically tuned just for SSO, it's relatively easy. But then you have other problems like the large signal stability, inertia response, and so on, which tend to sort of pull these control parameters in different directions. So you need to make sure that you are able to design the right trade-off. And often you need higher degrees of freedom in your controller to achieve that. So we are working on that aspect, and also rethinking some of this IBR control to have stability guarantee at a global level with minimal conservativeness. The next one is connection compliance, and we are working again with NESO on better representation of the grid in particular in those connection compliance process. so that it captures the risk of SSO in a better way. Then if some oscillation slips through that connection compliance, are we able to track them down close to real time by using digital twin or digital replica of IBRs? And even if we miss some of those oscillation events happen, can we use purely data-driven model-free techniques? So my colleague Yunji is working on a generalized dissipating energy flow method, and we are also working on something based on singular value decomposition, which is going to allow the time series to be converted into something like an A matrix for analyzing the root cause. So these are purely data-driven with no reliance on any simulation model. And
we have 8 minutes left for the whole thing.
And this is the test bed. So this is my final slide anyway. This is the test bed that we are developing for validating the findings of all those 4 aspects that I talked about. And hopefully we are discussing this with NESO. We can possibly make it open source by, of course, masking the names of the substations as a general test bed for SSO research. I'll finish off with these takeaway points. Thank you very much. Thank you. Sorry, Julia, for overshooting.
No worries. You'll have more questions to answer offline. That's all.
Okay.
Thanks so much, Balarko. So I'll start with questions right away. How was it determined that the IBR caused 8 Hertz oscillations in Scotland in the summer of 2021?
You mean what's the method they used to determine?
I guess the question is, yeah, kind of how it was determined that IBRs caused it. I guess the question maybe is why it was decided that IBR caused it.
I think one of the things that I heard is that they looked at the phase angle between Q and V and used that as one of the methods to sort of figure out where that sort of sensitivity or the phase relationship was what was not expected, and used that as a measure to determine that that was the sort of the bad actor.
The next question is, in injecting the disturbance signal, do you use a single frequency or multi-frequency signal, and why? Is it done using EMT simulation with black box models? We
use multi-sign or pseudo-random binary. These are 2 reach signals that are typically used for system identification. And what we do is that we inject this in not an EMT ABC, but an EMT DQ model that we use here in MATLAB Simulink. And we inject these signals into that model, get the terminal measurement, the voltage and current, and then apply the method that I described.
Got it. The next one is the logic of current input voltage output modeling the same for both grid forming and grid following IBRs?
Modeling wise, it could be the same, but in terms of what a GFL control and what a GFM control, of course, they are different, because a GFL typically controls the injected current and its phase angle based on the voltage magnitude and phase angle on the bus. And GFM is just the mirrored image. So it basically controls the voltage and phase angle on the bus based on the current that's injected into the grid.
Thank you. What difference does it make to modeling the IBR/synchronous machine as voltage source/current source? Is it a scalability issue?
Well, I mean, I don't know if the angle is how the network sees it. I mean, obviously, even for an IBR, if I understood the question correctly, even for an IBR, you can do a sort of current injection model on the network, like what's usually done for synchronous machine. But it's just that because we have we consider the LC filter and the other side, including the transformer as part of the network, we used a voltage injection framework. But it's not to say that either way is sort of set in stone. We can do it both ways in terms of modeling. I mean, what the resource or the device is controlling is a different thing. So I hope I was clear on that. I mean, modeling wise, it's what's the input to the grid and what is basically coming out of the grid.
Right. Can you please elaborate on EMT DQ approach? How PLL dynamics are considered in EMT DQ representations?
EMT DQ essentially is, we are considering the synchronously rotating DQ reference frame. And of course, we are assuming narrowband signals. So we can basically consider everything to be centered around the fundamental frequency. So we're not going for something like a dynamic phasor with multiple frequency bands. So assumption is that this is narrowband, and then you go from space phasor to your D and Q axis voltages and currents.
Do you see a trend where with more grid forming, it was kind of like one of the last slides that you mentioned, do you see a trend where with more grid forming, there is better agreement between EMT and phasor domain simulations, or there is no correlation?
It all depends, or it depends to a large extent on the grid strength, what it pans out, and also the control bandwidth. So, I mean, these things change a lot depending on the interplay between the grid strength and the control bandwidth. So I don't think we have a one-word answer, but from the trend that we have seen in some of these IEEE test systems is that higher the share of grid following for a given bandwidth, again, I have to say that, the difference between EMT and RMS is less, and it sort of goes up when the share of GFM is higher. But again, I mean, this is for the specific bandwidths that we chose. This conclusion can sort of move depending on the bandwidth.
The next question is, could you share a bit more detail about how the system identification is performed on slide 16?
So in terms of how was it done, we used the system identification toolbox that's available in MATLAB. So it's the traditional system identification where you put a injection or a probing or a perturbation signal, you tap some measurements from the system, and as long as the excitation is strong enough or rich enough in terms of exciting the dominant modal components, you are not violating the linearity, so you're not sort of drifting away from the operating point, or you are not hitting any of the limits, then you are expected to get reasonably good accuracy in system identification. But the key here is the choice or calibration of that perturbation input. So that's the key.
All right, so the last question that I'll ask online is, how is the digital twin on slide 24 envisaged, as the fundamental challenge of model availability still remains a blocker?
Well, the digital twin is to get around this challenge of model unavailability or opaqueness or lack of transparency of IBR models. So can we have something like a replica, which is not going to be following exactly the same structure which is there in the vendor specific model, but still can capture the operating point dependency, how this IBR black box is operating from the input and output relationship, and basically track the behavior like what a digital twin typically does. How exactly this is going to be implemented is something that we are working on. So there are some methods that we are sort of playing around with, especially with our experts in the control community who are sort of developing digital twin for other applications. But yeah, I mean, how exactly this will be done and is something that we are working on. Thank you.
Thank you, Balarko. Okay, so we're at the top of the hour, so we're going to wrap up now. Balarko, thank you once again for a very informative presentation. This work will continue, and hopefully we'll hear more about it in the future webinars. In the meantime, I encourage you all interested, all interested people in Oscillations work to keep an eye on Balarko's work for the future, because obviously it's still ongoing. As I mentioned earlier, an email will go out once the video file has been posted, and we'll get the responses to your all unanswered questions answered and posted as quickly as possible. We appreciate your engagement, and if you would like to stay engaged, we invite you to participate in the next ESIG webinar on December 3rd, where Elevate Energy Consulting will cover another hot topic on IBR and data center integration, updates from 2024 and predictions for 2025. Further information on all ESIG webinars can be found on our website, www.esig.energy, under events, and you are all invited to attend. Information on all G-PST webinars can also be found on www.globalpst.org. Balarko, I would like to thank you once again for this timely webinar, and also for taking time to talk to us in the evening, your time. And we look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Goodbye.
Thank you, Julia. Thanks, everyone.
Bye.
Thank you. Bye.